there's a whole theory and science behind quarks, but in this short kind of intro to what a quark is, I really just want to discuss the approach that I've taken to change the quark charge calculations and the implications of that. So I'm not going to go into the theory or the discovery of quarks as a model, but I'll just kind of outline aspects of the model that I've been developing on the basis of changing quark charge calculations and give you kind of the fundamental reason why I've done that. So quarks are the fundamental particles that are present in a proton and a neutron. And as I mentioned previously, the proton and neutron and electron are really the atomic theory that biology uses to understand molecules and atoms, and all of the kind of biological complexity associated with that kind of materialistic perspective. So in hydrogen we have a proton and an electron. It's the most simple atom of the periodic table, and the proton contains in its nucleus 3 quarks, and the quarks in this model of the normal kind of atom that we've considered in biology contains 2 up quarks and 1 down quark. Here the up quark is highlighted in red and it has a charge of plus 2/3, and the down quark is highlighted in blue and it has a charge of a negative 1/3, and we add those together to get a +1 proton and a 0 charge neutron. Okay, so that's the standard thinking. So that thinking gives us baryonic asymmetry. It provides a way of understanding atom theory on the basis of stability, and it also provides a disconnection between cosmology and atomic theory. So there are a few things that one can consider, and you know, it's a challenge to go from, well, neutrons are a 0 charge and protons are positively charged, and they're both found in the nucleus of an atom, and so there's this overall positive charge in the center of the atom which, well, like charges repel. So the idea that like charges repel would suggest that the 2 positive charges in the center of the atom and the nucleus would cause repulsion, and that repulsion is overcome by a force called the strong force, and the strong force has some very interesting properties, but in biology we just ignore that, and we say, well, a neutron is 0 charge and a proton is +1, and the center of the nucleus is always positively charged, and the electron on the orbital layers around the atom is negatively charged, and never the twain shall meet, right? So a negative and a positive are attracted to each other and should bind, and yet we see that the electron and positron, proton are kind of separate, and they don't connect, and we have 2 positive charges in the middle for helium and 2 negative charges on the outside, so overall we have an atom with 0 charge. So that's really kind of the standard thinking. The standard atomic model has no positrons in it, which is the antimatter that I mentioned before. So in the new kind of quark model of it's really a boson type model. I will need to explain what fermions are and bosons. A fermion is a like a type of particle that can't occupy the same place in space and time as another fermion. So it obeys a rule called the Pauli exclusion principle. And so that means that two electrons can't be in the same energy level at the same position within the structure of the atom, because their negative charges will repel one another and they can't occupy the same place. A boson, on the other hand, doesn't obey those kind of exclusion principles. It has a different property which allows it to kind of be overlapped, and so photons of light, and a laser light is an example of bosons, where there's a coherent aspect of bosons. They can all kind of overlay one another and look very similar. So my I guess quark charge model takes concepts of bosons and ignores the idea of the Pauli exclusion principle because of the boson-like properties. And I don't use fractional charges because I want to have a way of understanding how there's a relationship in the charge of a quark and a relationship with the charge of the electron, and a relationship that is called charge parity. So in the current standard model, we do not have charge parity. What we have is a disconnection between the charges in the quarks and the charges on the electron. And in this new boson-like model, we have charge parity, where the up quark, the red up quark, has a charge of -1, and therefore you would say, oh, it looks like an electron. And in the down quark has a charge of +1, and you go, oh, okay, that looks like a proton. Well, in this case, it looks like a positron, which has a charge, which is the antimatter particle of the electron, but it has the opposite charge, the same mass. So we can then understand that in the center of the atom, the proton is made of the 3 quarks, 2 up, 1 down, just the same as the standard model, but the charge is different. The charge for the up quark is -1, the charge for the down quark is +1, and if we multiply them, we still get an overall charge of a proton of +1. But in the case of the neutron in this new charge model for boson statistics, what we get is 2 down quarks, 2 pluses and 1 minus, multiply them together, we get -1. So here in this new model, a new atomic model, bosons within the nucleus of an atom, we have neutrons that are -1 charge. And so the difference between the new quark charge calculations, which have charge parity, and the old one is I'm using whole numbers and multiplication. The old way is to look at fractional charges and adding. And what I get is a -1 neutron. And to make my neutron the same as the neutron in the standard model, I add another particle into the mix. I add positrons, which is the antimatter particle, back into the atom structure. So my neutron plus a positron gives me an overall 0 charge, which is what we have in the standard model. So now I have what's called a mirror symmetry model, or a matter-antimatter symmetry model, which is what baryonic symmetry is. So baryonic symmetry is the same number or amount of matter and the same amount of antimatter. So that really helps in understanding the process and the logic behind understanding how the universe utilizes baryonic symmetry, which is an equal amount of matter and antimatter. And remember that one of the major problems that we have had in the existing kind of framework is that we're missing antimatter. And so I've resolved that problem through this new quark charge calculation. And we've resolved baryonic symmetry in doing so, which allows us then to kind of go, oh, so the hot Big Bang nucleogenesis baryonic asymmetry model no longer applies. So then we can kind of start again to think about cosmology from the perspective of this symmetry state of matter and antimatter. And as you can see with helium, I now have two positives in the orbital layer as well as two negatives. And I have an overall neutral charge for the atom as the number of positrons equals the number of electrons, and the number of neutrons equals the number of protons. So that's what I call a baryonic symmetry atomic theory. And that is the basis for looking at and understanding the photon geometry, or the electromagnetic field within atomic structure. Okay, so we will explore that in a later video, but this will give you at least the functional geometric change that is fundamental to start understanding the new model that I've been developing for quantum biology. So I call this supersymmetry inversion, right? So there's a mirror symmetry inversion process. So if you have a look at the helium structure on the left there at the bottom, the negative on the orbital outside has a positive on the inside, and the negative on the inside has a positive on the outside. So you can see that there's this matching of opposites and charges, which equates for, you know, a balanced state. So that's the point of equilibrium. The baryonic symmetry state provides an equilibrium point. And it's that point that's important, because that gives you an overall zero charge within the structure of the atom. And if we want to look at the beginning of the universe, we need to understand the zero charge state of the original universe, and the consistency of charge parity with the beginning of the universe is very important. We need to consider how the universe creates charge from no charge, and we need to understand how mass is created from no mass, and we need to understand how space is created from no space, and we need to understand how time is created from no time. So when we start to explore the model from those kind of really foundational levels, we start to then get a better understanding and comprehension of atomic theory. And that's really what I want to offer in terms of the connection between cosmology and biology at atomic level.